Okay, now what we're going to talk about is I worry anytime I don't see something making a Here we go. So what we know here is that we have a circuit and it has a 120 volt supply, which we can read with a meter. We have a current flowing into this circuit of 2.4 amps, and we have read, before we did anything else, we read the resistance of the windings of this motor, and the total resistance was 42.5 ohms. So this is a single phase motor, and from these three pieces of information we can find out almost everything about this thing, right? So first of all, we want to find the impedance, which is the hypotenuse of the resistance triangle. And we want to come up here and we're going to divide our 120 by 2.4 amps. And that'll give us our total impedance, which from what I've heard is 50 ohms. So let's plug that in. Can I switch colors somehow? I don't suppose. I can't figure that out quickly, so we'll just...
Yeah. Where's that? Right there, this A thing. The font is, yeah.
Good. Like that. Thank you, guys. 50 ohms of total impedance. Okay, everybody with me so far? Now, that means that we can also multiply up and we can get 120 times 2.4, and that'll give us our apparent power. And that's 288 VAs. Is that correct? All right. So now we have some information about this circuit, right? But one of the things we want to know is how efficient is this circuit? So first of all, our hypotenuse is what?
The impedance.
That's the impedance. So let's go over here and we're going to type in this little triangle here that we have 50 ohms of impedance. So that only leaves us one thing, right? That leaves us our side opposite, and we don't know our angle yet, do we? Our angle theta is something we need to know. That's our phase angle. We need to know the phase angle because we're going to go on and do another triangle. We're going to do the power triangle to find out how much power this thing can crank out. So the first thing we want to do is, what function do we have here? If we have the hypotenuse and they have the side adjacent, we have what angle? Or what function, I should say. We have the cosine. So on our handy-dandy TI-30X2S, we would hit clear a couple times, and then we would put in second function cosine, and cosine is A over 8. So the A is 42.5, which we'll put in, divided by 50. And our cosine, or our angle that we have the cosine of, is 31.788 degrees. So let's put in that the theta here is 31.788. Let's go one more number and we have a 3. 783 degrees. All right, everybody okay with that? Yes?
Yep.
Okay, good. Now let's draw a little, this is our angle right here. And that's our 31.788 degrees. Now, if that's true, we'd kind of like to find our side opposite, right? Now, one of the important things I said to you just the other day was when we went over this thing the first time last week. It was that when you're looking for something, you want to find a function where you have 2 out of the 3 things, right? But now that we have the angle, we have all of our functions. So we can say that we have all of our functions, sine, cosine, and tangent, and we're looking for one that has the opposite, which we're looking for, and the hypotenuse or the adjacent, which we already have. So we have the angle, so we have sine, cosine, tangent, and we're looking for one that has the opposite and the hypotenuse, because we have those, right? So we might as well use that one, right? So let's take the sine of this thing. Now we have our angle in our calculator, right?
Right.
31.788. So now we're going to just put in sine, second function answer, enter, and it tells us it's the sine of the angle. Let's come over here and we'll put sine of theta because we want to save this information, right? Okay, where is our symbol? I've forgotten how to insert our symbol. No, that's not it. Where was my symbol?
You just copy paste one from the top left.
Or I could just do that. Okay. Sine of theta is equal to 0.52678. 526.7, and we only need 4 digits. But if we leave this number in here, then we can play around with it. And it's in our calculator right now, right?
Yep.
And so now we could take our formula where our sine is this number right here, right? How do I get back into this thing? It's not going to cooperate. All right.
Could you drag it over?
No. Let's see. Well, anyway, we'll just come over here and start writing again. How's that? So our sine is 0.5726, which is equal to, what do we know about that? It's the O divided by the hypotenuse, right? The opposite divided by the hypotenuse. Now we know one of those. So we're going to say that is equal to the opposite, which we're looking for, divided by the hypotenuse, which we know is 50 ohms. Okay? So now we're going to come back here and take this O over H, and we're going to plug in 0.5267. 5267. And now we have if we have, did I put a minus in that? Sorry. So if we have 0.5267 is equal to 0 divided by the opposite, not 0, the opposite divided by 50, we can multiply both sides by 50, and 50 will drop out of the other side, right? 5267 is equal to the side opposite. Everybody agree with that? Because if we multiply both sides by 50, opposite divided by 50 times 50, the 50 will drop out completely and we'll just be left with the side opposite. So now we have that number, except we have the whole long one, 0.526782688, and we're going to multiply that times 50, and we're going to hit enter, and we get 26. Let's see, I want to grab all this, right? Oops. Instead of retyping it, sorry. I'm lazy. Or at least I don't want to keep retyping that. And now it's 26.339. 1. All right? And that is our opposite. So our side opposite, our x sub L, back to normal. How do we do that? There we go. And that's equal to, I told you this would be a learning process, 26.3391 ohms. And that's our inductive reactance. Now we want to have a new triangle, don't we?
Yes.
We want to have a second triangle. Oops. Let's see if I can do this. I doubt it. I'm in. Okay, let's just go back and get that slide again. Guess not. Okay, so we're going to have a new triangle. Just going to have to draw another triangle, not a big deal. And we know this one's a little bit bigger because the sides are a little bit different. Something like that. And this time, this is going to be our power triangle. So now we're going to have the apparent power is going to be our hypotenuse, right? Everybody agree with that? So the apparent power is 288 VAs, right?
Mm-hmm.
Okay, so that is our apparent power. Now, what we're really interested in here is our true power, right?
Yes.
We may want to know our reactive power, but for the moment we're more interested in getting our true power, our actual cranking force that we're getting out of putting in 288 VAs. To find that, we're going to go to the cosine, and we're going to see that the cosine of this angle, now we found the angle before, didn't we?
Mm-hmm.
Well, let's go back to that. And let's go back to second function cosine 42.5 divided by 50 to get our exact angle, which is 31.7883. And now we're going to take, well, we just found the cosine that has that. We could have just divided 42.5 by 50, right? Somebody say yes.
Yes.
And that means that this thing has an 85% power factor, right? So cosine second function answer, enter, and it says 0.85. So the cosine of this angle getting better at this, I think. A little bit faster. Is 0.8500. And that means that 85% of the incoming power is going to be turned into true power. Now, you're asking yourself, now how do we figure that out? Well, because the cosine is equal to, how do I add it? There we go. Yay! Come on. No? It's not going to let me do that. Come on. I don't know what it just undid, but okay. Edit. Text. It's not going to let me do anything. All right. So our cosine is 0.85, and the cosine is the A divided by the hypotenuse, right? So we can say that 0.8500 is equal to, what is A? We don't know. We're looking for that, right? So it's A divided by and our hypotenuse is what? 288, right? It's in this case, it's the hypotenuse of this triangle is our apparent power. So now, if we just multiply both sides by 288, what will the right side look like? The right side is A over 288 times 288. Everybody agree with the fact that the 288 will drop out and we'll be left with A is equal to 288 times 0.85? In other words, the hypotenuse times the cosine of the angle will give us the side adjacent. Is that correct? Well, I just happen to have 0.85 in my calculator, so I'm going to multiply times times 288. And I can't see if that came out correctly or not, but we'll find out. Yep. So our side adjacent is 244.8. Is it VARs? Is it VAs? No, none of those. It's watts, real live cranking power. So we're going to come down here and say that we have 244.8 watts. And that's the cranking force. Now, how much energy was wasted jumping up? Remember I described that VARs was sort of like loading a spring on a pogo stick. You could spend a lot of energy jumping up and down, but it doesn't get you any steps forward, right? Well, that's the same with the VARs, or I should say that was a good description of the VARs. I kind of like that. And so we might want to know how much energy is being wasted on that. Well, look at this. We still have the sine, don't we? And the sine is equal to O over H. And if we multiply both sides of that by the hypotenuse, we get the sine, which is 0.5267, right? Let's put that in here. 0.5267 times, if we multiply both sides of this by the hypotenuse, we'll get the hypotenuse over here, right? And the hypotenuse is still 288, right? We'll be left with nothing but the O on the right side, right? Everybody agree with that? In other words, the sine times the hypotenuse gives us the side opposite. Anybody want to agree with that?
Yes.
Maybe? Okay, so the result is that we have 155.6896 bars. Do what? Oh, yeah, I'm sorry, 151. There we go, 150, I wasn't reading the calculator correctly, 151.6896. So now, we've found out everything we can find out about this circuit. So just from knowing things we could read, like the ingoing voltage, the ingoing current, and the resistance of the circuit, the real true DC resistance, we can find the phase angle. And if we know the apparent power coming in, we can find the real live cranking force that this circuit is going to turn out. This motor or this circuit is going to crank out. Okay? Is that clear as mud to everybody?
Yep.
All righty.